This is the super review problem for rotational dynamics stuff. So I've asked 6 different questions on it. I have a rotating rod rotating about its center here, and I'm given a formula for the moment of inertia that comes from that. And I think I've labeled everything in the graph. I have the mass of it, I have the length of it, I have the final angular speed of it, but I noticed that that's in rotations per minute. So I'm going to go ahead and fix that right now. So 200 rotations per minute. I'm going to go 1 minute for every 60 seconds, just doing a little unit analysis problem, and then 2 pi radians for every 1 rotation, so the rotations are going to cancel. And when I crunch the numbers on this, I get 20.94 radians per second, just trying to keep a little more precision than usual since we're just starting out the calculation. The other thing I want to do up here before I really get into these questions is to get the moment of inertia of this rod. So I have 1/12 times the mass of it, which is 1.8 kilograms, times the length of it squared. And when I crunch those numbers, I get 0.5415 kilogram meters squared. All right, let's get into the questions now. So I want the angular displacement, and my first thought when I see that is to write down theta equals theta naught plus omega naught t plus 1/2 alpha t squared. But unfortunately, we don't know the angular acceleration. Now we could get it, and in fact, we're asked for it in part E, but I just wanted to take the opportunity to illustrate that there's a formula that gets this done for us, so a kinematics formula, without having to know the acceleration. So the displacement, the angular displacement, is going to be the average angular velocity. So I mean an arithmetic mean here, multiplied by how much time has gone by. So the left-hand side that I just wrote down, theta minus theta naught, that is the angular displacement delta theta. When I plug in my final angular velocity, that's 20.94. My initial was 0, so I'm not going to write it. Take 24.94 over 2 and multiply it by the total time for the process, which was 5 seconds. When I do this, I get 52.4 radians of total rotation as this thing is speeding up. In part B, I want to find the final tangential speed at the tips of the rod. So one of those tips is coming at us and one is going away from us. And those are at the edge of a rotating rigid body, so I use the formula V equals R omega for that. And the radius, that's going to be half the length, so 1.9 over 2. And omega, 20.94. And when I get a number on this, it is 19.9 meters per second. In part C, I want the final rotational kinetic energy in the rod. And rotational kinetic energy is given by 1/2 I omega squared. Again, in rotational dynamics, the moment of inertia plays the role of mass. And of course, angular velocity would play the role of velocity, or angular speed plays the role of speed. So this looks just like 1/2 mv squared. I already have I. I already have omega. When I crunch those numbers, I get 119 joules of energy. Part D, compute the average power input of the motor. So the motor is what's given energy to this rod. And it's given 119 joules of energy to that rod in 5 seconds. So power is the rate at which energy is transferred, or you could say the rate at which work is done if you like. And the total energy transfer was 119 joules. And the time it took was 5 seconds. And a joule per second is a watt. And this simplifies to 23.7 watts. Part E, compute the average angular acceleration of the rod. All right, I just look at the change in the angular velocity divided by how long it took. And the initial angular velocity was 0, so this is just going to be 20.94 over 5 seconds. And I get 4.19 radians per second squared. Part F, compute the average torque exerted by the motor. All right, so we don't have forces and lever arms to work with here. What I have to do is infer the force based on how fast this known moment of inertia is accelerating. So I write down torque equals I alpha. I is 0.5415 kilogram meters squared. Alpha is 4.19 radians per second squared. And I end up with an average torque. I suppose I should put a bar over it. I end up with an average torque of 2.27 Newton meters.